Started so we don't so we stay on schedule, and Diana keeps me in line here. So again, thanks for joining us. Our first presenter is going to be Oscar Ojeda, and Oscar worked with Pablo Cavaltieri, who is in the back. So Pablo, thank you for supporting Oscar and his research. Oscar's presentation is going to be on the development of 3D printing techniques for extraterrestrial infrastructure development via the ISRU.
Well, thank you so much for joining us today. Thank you for being in the presentation. I wanted to do a different introduction. I want to tell you today a story about what is the importance of this work. I worked with Professor Pablo in a group that works mainly on materials and architecture of materials, and I work on development of 3D printing techniques focused on the development of extraterrestrial infrastructure. I'm going to talk to you today about three projects that I worked in, very briefly, that are technologies that are possible turning points that will allow us to do the colonization of space. So why Mars? Why space? There are three main reasons. I'm not going to go deep in those. But the first one is related to the exploration. Yes, and the development of science, what we can do in space. The second thing is that space is of economical interest for many reasons, and in the future is going to be even more. And the third reason is for improving life on Earth and for guarding life on Earth, because the developments that are made in space or for space allow us to improve the quality of our life. So first, the first chapter is going to be about the main project I try to do. And it's about two machines that I helped develop with my grad student that couldn't join us today, but I'm very grateful with him. This is a cement paste extruder, a cement paste printer. Cement paste is of interest because it's a material used in infrastructure, used widely in infrastructure. So it has certain characteristics of high viscosity. It can be modeled as a Bingham fluid, which means that it's not non-linear, but after some point it becomes like with a linear behavior or a near linear behavior. And the main focus of the project is to study the material architecture. This is how is the material shaped based mainly on bio-inspired structures, like the shell of a part of the shell of the shrimp, mantis shrimp. So 3D printing allows us to do a lot of new developments and go beyond the material to try to improve its characteristics. So the first setup that was made was in a printer that already existed, and we made some improvements to it. I'm going to show it to you in the next slide. So the improvements were mainly three. First, we implemented a system of sensors which allow us to characterize better the process of printing. These sensors relate position towards in the printing and the pressure that is being exerted on the printer to improve the characterization of how the fluid is changing and how the flow is changing. The next part was to develop a syringe system, a metal syringe system that currently there is one that it's made of plastic. So this syringe will give a reusability system, will improve the characteristics of the flow because of the shape on the tip. We made some CFD simulations, very basic CFD simulations on how this improve the shape and the flow, and we would improve it and towards the printing. This is the setup, this is the printer, and this is the other improvement we made. And it's the development of a frame that allows us to position the injector in different positions. And this allows us to, without this graph, I'm not going to go deep in it, but it shows, the results show that there is no major change in the characteristics and the properties of the printed material, so it can be used in several positions. The next machine was the knee printer design. That these are the parts of a 3D printer. First, a mixer, a pump, the tubing, and a 3 degrees of freedom printer for our development. So the second part of the project was related to the design of this machine based on commercially available systems. So we selected the commercially available elements and made the final setup. The printer was this 3 degree of freedom, a net A8 printer. It was simple, it had an auto configuration that allowed us to work a lot on it. It's low cost, and even we're currently working on improving another one to print in 2 materials. The pump, this pump is as big as my hand, and it's fun because it costs $3,000, and so it's a very, very beautiful piece of equipment, and it's a high precision cavity pump that allows us to control very precisely how the cement paste is delivered into the printing system. Additional setups were made, pieces were designed and 3D printed, and it is fun because we are building a 3D printed 3D printer, so this is something that some people find interesting. Now I'm going to talk to you about another thing, that it's how we can use resources that are already available on site, and it's this. We want to build, this is the future we venture in space. So we want to be able to improve this because launch cost is high. So every kilogram we send into orbit costs as much as $10,000. So that's about what a kilogram of gold is costing right now. So that's why it's turning dirt into gold. Because if we can use this dirt, this Martian soil, that we have samples here of simulants, we can reduce a lot the cost of launch. So the destination, Moon and Mars, has these resources available, and these resources serve to other purposes such as radiation improvement. Radiation protection improvement. So what we did with this was we run a characterization in several terms. We measured its density, the particle size distribution, and its behavior when mixed with water. And so from this point, we started to work on the mix design of another process that will allow us to build infrastructure with this. We suggested 2 types of processes, although we could only, because of the time, and the main project was a printer again, to work on one test. It was to develop this geopolymerization process with Regolith. So I'm not going to go deep in the geopolymerization process, though. It allows us to build infrastructure with a different type of cement. So we try to use this regolith in order to build these bricks. We couldn't test them because they had some inclusions, so the idea is to, this week, make the final tests for it. And the last thing is about a project that we devised. There's a funny thing about Mars, and it's that sunsets are blue. So in the red planet, the sunsets are blue, opposite here to the blue planets, and the sunsets are red. So if we want to go there and we want to explore, this exploration requires mobility. And this mobility, with current paradigms, requires wheels. So we cannot take a rubber wheel and an air wheel to Mars or to the Moon. So we're going to need these characteristics. We're going to need durability, because they're going to be in a harsh environment for a long time. We're going to need high deformation to comply with the off-road type terrain with rocks and edges and cliffs. We need them to be easily maintainable so that we can make this maintenance on-site, and they require high traction. So we made this design that, and we 3D printed it. with using an architecture that is called PXEM. This architecture allows for a high deformation, and as you can see in this very basic, again, finite element analysis, we have a high deformation, but the point here is that no point, although it has high deformation, no point has a higher stress or a plastic deformation, so we can recover from this deformation. So the architecture plays a major role in this type of structures. So, of course, I want to acknowledge the program for the university, the Universidad Nacional de Colombia program UREP-C, and my advisors, and the grad students I work with, Reza, Lee, Vanessa, everyone who is here and who's not. I have no words to thank you for this opportunity and for welcoming into your lab. So, thank you so much. I have two quotes there in terms of doing things because they are hard and doing things because you believe in them. So I'll be more than happy to take your questions if there are any, and further we can discuss technical details if you want to. Thank you so much.
Okay, we have time for about one or two questions. So I know it's early. It's the first one.
Oscar, thank you for your presentation. That was very interesting. I was wondering because I saw so many things, and it's so special that you were able to participate in all that. So I was wondering, how does it work in your lab? That you are able to work in different projects? Like, how do they manage it?
How do I manage it? No, the point is that I have the fortune that Professor Pablo is very flexible, and he likes to explore new things. So as the main project with Reza was to build the printer, we had these different ideas, and we had the opportunity to explore them and to try to. It required a lot of work. I would have loved to be able to work more on these ideas. Actually, this wheel, we're thinking about, I got selected to participate in a Mars analog simulation this January. So we're probably going to test this. We're discussing about the possibility of testing the device on site on an analog mission. So the idea is to keep going and to go with that.
Thank you so much.
So I think we're running out of time.
Yeah.
Well, I would like to ask you something. First of all, congratulations. I think it is so important and so interesting. But I'm wondering how to continue implementing your research in our university. Do you think that you can do it perhaps in any of the labs that we have that are not so many and perhaps not so sophisticated?
I'm glad you asked about that because as Professor Vizcarra knows, we've been having a process of 5 years with a group that is called Aerospace Research and Development Group in the university. We are presenting the group to Conciencias next period. So the idea is that we are actually doing things. The image in the video, the spacesuit simulator, was actually a project we made last semester. And we don't require that much technology to achieve things. We have been doing tests with solid fuel rockets, with telemetry, with satellites. We're developing satellites test bench in the university. So I think we are going to be able to keep going with the aerospace. And actually with Juan, we also have a couple ideas to see if they go through. But yeah, the idea is that it's a field that requires a lot of attention in Colombia.
Okay, thank you, Oscar.
Thank you so much.